It's been pretty incredible watching AI language models evolve. We've gone from like basic text generators to chatbots that feel almost human.
Yeah, and even AI that can write code now. It's wild.
Totally. And the engine behind most of this magic, it's usually something called left to right generation. Where the AI predicts the next word, then the next, basically building sentences like we might.
Exactly. These autoregressive models have been the real workhorse, creating text step by step. But imagine a totally different approach, maybe more like sketching a picture. Broad strokes first, then you gradually add the finer details.
Okay, interesting analogy.
Well, that's kind of how diffusion-based large language models, or DLLMs, work. It's this course-define idea.
Right. Let's unpack that a bit. So instead of just one word at a time, DLLMs generate text more like refining a blurry image until it's sharp.
That's a good way to put it, yeah. Models like LAD and Mercury are exploring this space.
And what's really caught my eye is that LADA, one of these DLLMs, has shown it can actually hold its own against those more, established models. Pretty competitive.
It is. And what's truly fascinating now is whether we can give these DLLMs the same kind of reasoning superpowers that the traditional LLMs have been developing.
You mean through things like reinforcement learning?
Yeah.
Where the model learns from feedback.
Precisely. Getting rewards for good answers, learning from mistakes, that kind of thing. It's been huge for autoregressive models.
So the million-dollar question then is, can we apply that same kind of reward system, the reinforcement learning, to boost the reasoning abilities of these DLLMs? Because they work so differently.
And that's exactly what this new research paper dives into. They've created a system called D1.
D1, okay.
Yeah, and it aims to enhance the reasoning of these masked DLLMs by combining sort of learning from really well-explained examples with reinforcement learning.
Gotcha. So that's our mission for this deep dive then, to really understand what this D1 framework is all about.
Exactly, how it actually works, its magic behind the scenes, and why this could be a really significant step forward in the world of AI language models.
Absolutely. Sounds fascinating. So let's start with the basics. What exactly is D1? What are the core ingredients here?
Okay, so think of D1 as a two-stage recipe. It's specifically designed to make masked DLLMs, like our friend LADA, much better at reasoning. It's a specialized training approach.
2 stages. Got it. What's the first part of this recipe, stage 1?
Stage 1 is supervised fine-tuning, or SFT. Imagine you're teaching someone a really complex skill, right? You'd show them lots of excellent examples, step by step.
Right, like a good tutor.
Exactly like a good tutor. That's essentially what SFT does. We take a DLLM that's already learned a lot about language, and then we fine-tune it, we train it some more on a data set that's just packed with high-quality reasoning examples.
And the goal is?
The goal is to really instill deep knowledge about reasoning and encourage it to learn how to actually think things through, not just spit out answers.
Okay, and what kind of examples are we talking about? Is it just like question, final answer?
Oh, much more than that. They use this special data set called S1K. It's got 1,000 reasoning questions. But here's the really key part. These questions come with incredibly detailed step-by-step solutions.
Ah, yeah.
And these solutions even show how to double-check the work, how to go back and try a different approach if the first path didn't quite work out, backtracking.
Wow. So it's like showing the model not just the destination, but the entire journey, including all the detours and corrections.
Precisely. That seems to be the idea, learning from the whole process.
That sounds incredibly valuable for teaching reasoning.
It really is. And because we're dealing with these masked DLLMs during this SFT stage, they also use a masking technique.
Right. You mentioned masking.
Yeah, it's like having some words in a sentence covered up, and the model has to figure out what those missing words are based on the surrounding context. This just further strengthens its understanding of language and how reasoning unfolds within it.
Okay, so stage 1, learning from a brilliant tutor who shows all their work. Makes sense. What about stage 2? You mentioned reinforcement learning.
Exactly. The second stage is where reinforcement learning, or RL, comes in. They use a new algorithm they developed called Diffusion-GRPO.
Diffusion-GRPO, okay.
Now, you might have heard of RL, where an AI learns by getting rewards for its actions, right? Like points in a video game.
Yeah, learned by doing, basically.
Sort of. This stage lets the DLLM actively learn what makes for good reasoning by getting that kind of feedback, rather than just passively learning from static examples like in stage 1.
So it's like it's actively experimenting and gets a little good job signal when it reasons effectively.
In a way, yes. But Applying this reward system to DLLMs, well, it isn't quite as straightforward as it is for those standard left-to-right models. There are some unique challenges involved.
Okay, here's where it gets really interesting, I bet. What makes it so tricky for DLLMs? Why can't you just use the same RL techniques?
Well, the traditional RL methods that work so well for those word-by-word models, they often rely heavily on being able to easily calculate how likely a whole sequence of generated words is. The log probability of the sequence.
Okay.
And that's relatively simple when you're building the sequence one word at a time. You just multiply the probabilities. But DLLMs, they generate text in this more holistic way, refining it over several steps.
Right, that whole course-defined thing.
Exactly. And that makes it much, much harder to calculate that overall probability for the entire generated text.
Right, because they're not following one single predictable path to the answer. Okay, so how does this diffu-GRPO thing overcome that hurdle? What's the clever trick they're using?
So the core innovation here is a really efficient way to estimate the likelihood of each individual word or token within the generated text, not the whole sequence at once.
Estimate per word. Okay.
And they do this using something they call random prompt masking.
Random prompt masking. That sounds like a puzzle. How on earth does that work?
Okay. To get this, let's quickly revisit how these masked DLLMs operate. Remember, they have this process where they gradually hide words in a sequence.
Yeah, based on that noise schedule, like a dimmer switch.
Exactly like a dimmer switch. So at the beginning, T0, all words are visible. As T increases towards 1, more and more words get covered up with a special unmasked token. By the time you get to T1, the entire sentence is hidden. Total blackout.
Okay, clear sentence to total blackout. Got it.
Right. And the model is trained to do the reverse, to take a partially hidden sentence at any stage T and predict the original unmasked words. Now, that noise schedule, it determines how likely a word is to stay visible at a given step P.
And LVA uses a simple linear schedule.
Yeah, for LOD, it's just up 1 T at a steady rate of hiding. And importantly, during training, the model's loss function only focuses on predicting the words that are hidden at that particular step.
Okay, so that's the basic mechanism of a masked DLLM. Prediction based on unmasking. Now, connect that back to diffu-GRPO in this random masking of the prompt. How does that help with the reinforcement learning part?
Okay, so diffu-GRPO needs to figure out how good the generated answer is, right? To give it a reward.
Yeah.
And to do that, it needs to estimate how probable each word in that generated answer is. But like we said, calculating the probability of the entire answer is too complex.
Right.
So they use a simplification. It's called a mean field approximation. It's basically like saying, okay, let's just estimate the probability of each individual word as if they're mostly independent of each other. It's an approximation, but it makes things tractable.
Okay, simplifying the problem by looking at each word's likelihood separately.
Got it. That's the core idea. And then, to estimate how likely a single word in the generated answer is, they use this neat trick involving the original question, the prompt.
Here it comes.
Right. So let's say the AI generated an answer to your question. To figure out how probable a specific word in that answer is, they take your original question and they randomly cover up some of its words with a certain probability. Let's call it P-mask.
They mess with the question.
Yeah. Then, while keeping the generated answer completely hidden, like at T1, they ask the DLLM to essentially perform one step of unmasking, but only for one specific position in the answer.
Just reveal one word in the answer.
Exactly. And the model's prediction for that one word, given the partially masked question, helps them estimate how likely the actual original word in the answer was at that position.
Wait, hang on. That's kind of mind-bending. They're perturbing the input question to understand the likelihood of the output answer. Why does that work?
It's clever, right? Yeah. The logic is, by randomly masking parts of the question, they're presenting the model with slightly different contexts each time they do this estimation. So when the model tries to predict that single word in the answer, it has to rely more on its internal reasoning learned during training and on the parts of the question that are still visible. This process slightly changing the question context, then taking just one unmasking step for one answer word gives them an efficient way to gauge how likely each word in the generated answer truly is, according to the model.
That's a really ingenious shortcut. And you mentioned the paper contrasts this with LAD's original method.
Yeah, the paper notes that the original LADA imprint uses a much more computationally heavy Monte Carlo estimation, requiring like 128 forward passes through the model just to estimate the probabilities for RL. This new one-step estimation using random prompt masking is way, way more efficient.
Huge difference, especially for RL, where you need to do this repeatedly.
Absolutely. Makes online RL much more feasible.
And why specifically random masking of the question? What's the advantage of messing with the prompt like that?
Well, they found this random prompt masking actually acts as a form of regularization, a built-in safeguard.
Regularization, how so?
It's kind of like showing a student slightly different versions of the same practice problem. By seeing these variations in the prompt, it helps prevent the model from just overfitting or memorizing the answers to the exact questions it saw during training.
Encourages generalization.
Exactly. It pushes it to learn more general reasoning skills. Plus, they argue it acts as a kind of data augmentation. You get more gradient updates, more learning value out of the same question-answer pair because each slightly different masking of the prompt leads to a slightly different estimation signal for the RL update.
Right, it's like getting multiple practice problems almost for free from one example. That makes a lot of sense. Okay, so now how does this clever estimation of word probability feed into the actual reinforcement learning part, this Diffu-GRPO algorithm?
So Diffu-GRPO builds on an existing RL algorithm called GRPO, which is known for being quite efficient. They've essentially adapted the GRPO objective function, the thing that guides the learning.
The reward function.
Yeah, the loss function that incorporates the reward. They adapted it to use their new way of estimating word probability specifically for DLLMs. This function also includes some important safety measures.
Like what?
Like a clipping mechanism, which basically prevents the model's behavior, its policy, from changing too drastically with each update. That helps keep the training stable.
Avoids it going completely off the rails.
Right. And there's also a penalty term, a KL divergence penalty. If the updated model starts behaving too differently from how it was initially, either the pre-trained model or the SFT-tuned one, it keeps it anchored.
So it's a carefully balanced approach as we encourage improvement, but don't let it forget everything it already knew or become unstable.
Exactly. And the overall Diffu-GRPO algorithm, described in Algorithm 1 in the paper, basically works in a loop. It gets the model to generate answers, completions, it computes rewards and advantages based on how good those answers are, using the random prompt masking to estimate probabilities. And then it updates the model's policy, nudging it slightly to be more likely to produce those good, high-reward answers in the future. This process repeats, iteratively improving the model's reasoning based on the feedback.
Okay, wow. We've really unpacked what D1 is and the cleverness behind Diffu-GRPO and that random prompt masking.
Yeah.
Now, for the big question, why does all of this matter? Did it actually work? What did their experiments show?
Yeah, the results are really quite encouraging. Their main finding is that D1 LAD, that's the LAD model, trained with both Stage 1 SFT and Stage 2 Diffu-GRPO, consistently outperformed the original base LADM model.
Okay, better than the base model. What about compared to just doing one stage?
Also better. It outperformed models trained with only SFT or only Diffu-GRPO across a range of reasoning benchmarks. They looked at mathematical reasoning like GSM-8K and Match 500, and also logical reasoning tasks like Countdown and Sudoku.
So D1, the combination, was the winner. That's a strong vote of confidence for their two-stage approach. Were the improvements, like marginal or significant?
In some cases, very significant. For instance, they saw really big improvements on the logical reasoning tasks, Countdown and Sudoku. The gains on the math problems were a bit smaller, but still consistently positive.
Interesting. Why the difference?
Well, they hypothesized that maybe the base LAD model, especially after instruction tuning, was already pretty decent at the math tasks, so there was less room for improvement, maybe hitting some saturation. Whereas the logical puzzles, which often involve more structured constraints and planning, might have had more potential for gains from the RL stage.
That makes sense. So maybe this D1 approach is particularly well suited for boosting those kinds of structured, logical reasoning skills.
That seems to be what their results suggest, yeah. Another really important point they make is about generalization.
Oh, yeah.
The improvements they saw with Diffu-GRPO weren't just for problems of the exact length they trained on, which was 256 tokens. They also saw performance gains for shorter problems, 128 tokens, and longer ones, 512 tokens.
So it wasn't just memorizing tricks for that specific training length.
Exactly. It indicates the model isn't just learning superficial patterns, but is actually learning more general reasoning strategies that it can apply somewhat flexibly to different situations and lengths.
That's a crucial distinction, isn't it? Suggests a real improvement in underlying capability, not just rote learning for the test.
Totally. And they also dug into the qualitative results, like looking at the actual reasoning steps the models produce, especially on those longer problems.
And what do they find?
They observed what they called aha moments in the reasoning traces generated by the models trained with SFT, and especially the full D1 framework.
Moments. Like what?
Instances where the model seemed to realize it was going down the wrong path and then actively went back to correct itself. Self-correction, backtracking, things you see in human reasoning.
Wow.
They noted they didn't see this nearly as often in the original instruction-tuned LLDA model.
So the D1 training seems to be encouraging more sophisticated reasoning behaviors, like double-checking and fixing mistakes on the fly.
Precisely. The paper even gives specific examples in the appendix. I think there's one about flags and another about a bakery problem, where you can literally read the step-by-step reasoning trace and see these self-corrections happening in the text generated by the SFT and D1 models. It really highlights the value of that initial SFT stage, learning from those detailed examples.
That's genuinely fascinating to see laid out. What about that random prompt masking part of Diffuse GRPO? Did that specific innovation prove to be as helpful in practice as they theorized?
Absolutely. They ran ablation studies comparing their random prompt masking to using a fixed masking pattern for the prompt during RL.
And
the random masking consistently performed better. It also allowed them to do more policy updates per batch of data. They use a variable for this without the training becoming unstable.
so more learning steps, faster convergence.
Exactly, which ultimately leads to faster learning overall and a more efficient use of computational resources compared to fixed masking or the very slow original LAA estimation method.
So that random tweaking of the initial question wasn't just a clever way to estimate probabilities. It actually made the whole reinforcement learning process smoother and more efficient too. Double win.
Triple win, really. Better performance, faster learning, and it acts as regularization. It seems like a really effective part of the Diffuse GRPO design.
Cool. Did they look at how much random masking was best? That mask value?
They did. They experimented with different probabilities for masking the prompt tokens. They found there's a bit of a trade-off. Too much masking might make the estimation too noisy, while too little might not provide enough regularization or efficiency benefits.
So there's a sweet spot.
Yeah. It looked like using lower masking probabilities, specifically 0.3 or less, so masking 30% or fewer of the prompt tokens, randomly achieved the best balance between training stability and final performance.
Interesting to see that kind of fine-tuning detail. Okay, and finally, the big picture. How does D1 LLDA stack up against other cutting-edge language models out there, both diffusion and autoregressive?
So they included a comparison chart, figure 4, in the paper. They compared D1 LLDA to other DLMs and also to some well-known autoregressive models of roughly similar size, like Llama 2 7B.
And how did it fare?
Pretty well, actually. Now, it's important to keep in mind that D1 LLDA underwent this task-specific RL training on math and logic problems, which the other models might not have.
Right, apples to slightly different apples.
A little bit, but even with that caveat, it showed strong performance. On the GSM-8K math benchmark, it actually achieved the top score among the models compared, and it got the second highest score on the Math 500 benchmark.
Wow, so it's really showing potential to be a genuinely competitive approach, especially on these reasoning tasks.
It really is. It demonstrates that DLLMs aren't just a novelty. They can be trained for complex reasoning. They did, however, note a kind of mixed trend when scaling sequence lengths on the countdown and Sudoku tasks. Performance didn't always keep improving with longer sequences.
Any thoughts on why?
They suggest a couple of things. First, these more complex logical tasks might really benefit from starting with an even stronger base DLLM. And second, there's a need for more efficient inference algorithms for generating those longer sequences during the RL training itself. If generating long answers is slow or noisy, it can hinder the learning process for those tasks.
That makes sense. The tools need to keep up with the complexity of the tasks you're trying to train for. Okay, we've taken a really comprehensive deep dive into this D1 research, fascinating stuff. What's the main takeaway message for everyone listening?
I think the core message is that these researchers have successfully shown a viable path to significantly improve the reasoning abilities of diffusion-based language models. It's not just for autoregressive models anymore.
And they did it through this specific combination.
Yeah, by cleverly combining that supervised fine-tuning on high-quality, step-by-step examples with a novel reinforcement learning method, Diffu-GRPO, that's specifically tailored to the unique way DLLMs generate text, using tricks like that random prompt masking.
And why is this important for the broader AI community? What's the significance?
Well, it's significant because it really opens up a new avenue for enhancing reasoning and intelligence in these non-autoregressive language models. Remember, DLLMs have potential advantages, maybe in inference speed or efficiency down the line.
Right, they generate text differently.
Exactly. So if we can unlock their reasoning potential using methods like D1, it could lead to potentially more efficient and powerful AI systems in the future. Faster AI assistance, maybe new ways for AI to tackle complex problems or generate creative content. It broadens the toolkit.
That definitely sounds like a really exciting future. And the researchers also pointed out some remaining challenges and areas for future work, didn't they?
Yes, absolutely. They were quite clear about that. They specifically highlighted the need for developing better, faster, more efficient decoding strategies for DLLMs.
Why is that so critical?
Because that would be crucial for enabling effective RL training with much longer, more complex reasoning tasks. If you can generate longer, coherent reasoning chains efficiently during training, you can potentially unlock even greater capabilities.
So this D1 framework is a really promising step, maybe even a breakthrough, but there's still plenty of uncharted territory to explore in optimizing DLLMs for reasoning.
Definitely. It's likely just the beginning. And that actually leads me to a final thought. Something for you and for our listeners to maybe ponder.
Oh yeah, lay it on us.
Okay, so considering that these diffusion-based LLMs create text in such a fundamentally different way, this course-defined refinement, rather than word by word, what other unique strengths or capabilities might emerge as we continue to explore and refine techniques like D1? Could they excel at different kinds of reasoning or problem solving that traditional LLMs struggle with? Maybe tasks that require more global coherence or planning from the outset. What new possibilities might open up as we get better at harnessing this different approach to language generation? It really makes you wonder about the different flavors of intelligence we might unlock.